All right, welcome back, everyone. Today we are going to continue our discussion on the chapter on floating car data. This is chapter 4 from the book Traffic Flow Dynamics. In our last meeting, we discussed about extended floating car data, where we not only have GNSS fixes from floating car data, which includes time, position, coordinates, geographic coordinates, but also extended data that include acceleration and gyrosensors data that tell us about speed and heading information about the cars. If we have radars or cameras on the vehicle, we also get information about the distance to and the speed difference from a lead vehicle. And we can also get more data from the position of the gas or brake pedals, activation of turning signals, and all the data that is collected with the controller area network communication interface that all cars have. And all that data is provided as a time series. So all of that is considered to be extended floating car data that we can get from modern um, communication interfaces and from the modern vehicles. And once the different filterings are applied to these multiple sources of the data, we can get a much rich source of data. And it is a lot of information that trajectory data does not provide us directly, but it is limited to the number of vehicles that are considered to be floating, the number of vehicles on which we have all these sensors for getting the data. So we saw this diagram the last time where we can see using the heat map, we can see the number of um, recorded positions of the floating car. I think there's a question. Yeah, kidding.
I don't think your screen is viewable. I just want to know.
Sorry.
I don't think I think there's a problem with your sharing your screen. It's black.
Okay, just a second. Do you see my screen for map matching now? What do you see on my screen now?
Me, I'm not if Saba is saying it's okay, no problem.
Let me know if there's any problem with, because we are going to refer to the chapter here. So let me know if you don't see the map matching page right now.
Can you please stop sharing and do sharing again because
Yeah,
I'm not able to see it.
okay. So I'm sharing my entire screen. Do you see anything now? So right now it should be sharing the Jitsi screen, but I'm going to switch to Zotero, which has my chapter opened. Now do you see it?
Just continue. It's my problem. I'll log out and enter again.
Okay. We'll wait for you. Okay. Meanwhile, I can check if we are still properly recording. We are good. Okay. Let's give Gideon a few minutes to come back and then we'll continue. Okay. Now do you see the screen?
Yes, yes. Now I can see it.
Okay, great. All right. So as we were saying before, we have discussed floating car data, which is GNSS fixes, which is based on geopositions which are timestamps. So we know that those are sequences of data. And we can also get extended data from different sources using different sensors on the modern vehicles. Now we are going to discuss map matching, which is the procedure of assigning whatever recorded geographic positions we are getting from the floating car to a digital map, which has a logical model of real road network. So what we want to do is getting the raw data from floating car data, we want to accurately understand what is the actual paths that the vehicle has taken. That is our goal with map matching, so that we know exactly what path was taken uh, while the vehicle was traversing that road network. And map matching has this example here where we have these 3 points. Let me try to annotate that here. So we have these 3 points A, B, and C. These are the raw coordinates that we are getting from the floating car data. Now, the goal is to determine what is the path that the vehicle has taken. So we want to see what that path could be. One possibility is, let me use this color. So one possibility is, given the points A and B, the vehicle may have traveled on this road. But then once we also get the coordinate C, the probability of the vehicle moving on this road network becomes very small because you cannot go to the location C if you were on this road network. Then there's a higher probability that you are actually traversing this path. And so the map matching algorithms need to determine these paths using two sources. One source is the geographic coordinates that we are getting. The second is the connectivity or our knowledge of the connectivity of this road network, which I've highlighted here. So we need to consider the sequence of points that we are getting from the floating car data. And we also need the knowledge of the connectivity of the road network to determine reasonable paths that the vehicle takes. So the paths that we are discussing here, these paths are not about what is going to happen next. That's a different problem. The problem in front of us right now is what is the actual path that the vehicle has taken and matching it on a digital map. So how do we do that? Map matching algorithms are two types. They are either real time or offline algorithms. Real time algorithms, like we have seen used by Google Maps, where it tracks where we are exactly on, on the map and can tell us from our timeline history where we were at a certain point in time, what areas did we visit. So all of that comes from real time algorithms. Offline algorithms are uh, they do post processing after the trip is complete, based on the discussion here. So the robust map matching combines, as I said before, the location data that we are getting and the knowledge of the connectivity of the road network for determining a feasible path. One of the algorithms that is used for map matching is called as hidden Markov model. Hidden Markov model is used in other applications as well, but here hidden Markov model, or HMM, is used to determine the state of the road segment, which means what road segment are you on at a given moment in time, and then what will be the next road segment where you'd go. And this is where we are getting the geographic coordinates continuously. As described in the book, it's between 1 to 2 minutes for real time. And for offline, I think it could be a different time interval. But given that HMM are used, We have hidden states of Ri, which are the road segments, which we want to determine using the algorithm. And we also have actual measurements, also called as state measurements, which are about the location points, z of t. So z of t are, for example, x1, comma y1. X1, y1 are telling us the geographic coordinates of where you are, and Ri is the road segment that we think you are on, given what we have about the location. So there are two probabilities that we need to estimate for solving the map matching problem. The first probability is called as emission probability, and this is given by the formula P of z of t given Ri. So let me switch here and let me write it here so it's clear what we are discussing. So we have the probability of z of t given Ri. Ri is the road segment. So it could be R1, R2, R3. We don't know what road you are on. Looking back at the plot that we saw here in figure 4.4, we have this yellow line that I drew on the map and the blue line. So we can say, for example, yellow line is R1 and blue line represents R2, the two different road segments that a vehicle could have possibly be on. So we want to know which one the vehicle actually took, R1 or R2. And Z of t can be represented using x1, xi, yi, because these are the geographic coordinates that we are getting from the floating car data. And so our probability is that, assuming that vehicle is on the road segment Ri, what is the probability that the coordinates that we got from the floating car data, we will get those coordinates? How likely it is that we will get exactly these coordinates if the vehicle was on Ri? So for example, if the vehicle was on this yellow segment, what is the probability that we get the value x1, y1? Or if the vehicle was actually on this blue road segment, what is the probability that we will get x1, comma y1? So let's now read the definition of the emission probability. The emission probability for each road segment P of z of t given Ri gives the likelihood that the measurement z of t would be observed if the vehicle were actually on road segment Ri. So we've already assumed that the vehicle is on a given road segment Ri, and we are looking at the likelihood that we would observe this value of z of t if the vehicle was on the road segment Ri. Any questions so far? So the next question is, how do we estimate these probabilities? According to the chapter, these probabilities are computed from the air distance between the measurement point and the projection of z to the road segment. So the measurement point that we have obtained is z, which is the geographic coordinate x1, y1. And then we also project that geographic coordinate on to the road segment on the map. So what is the air distance between them? That is uh, our emission probability. Now, Newson and Crum use a Gaussian distribution, also called as normal distribution, with a standard deviation of about 5 meters, using the assumption that this is the GPS noise. So Let's actually look at the first exercise in this chapter to make this more concrete, to try to understand how these probabilities are estimated. So that is on page number 45. And here is our very first problem. So here it says, assume a major straight road R1 along the x-axis of a Cartesian coordinate system y equals 0 and a smaller parallel road R2 at y is equal to 30 meters. Let's try to draw that. Delete this. And so here is our y-axis, and let's draw the x-axis. It should be straight. Come on. Okay. All right. So we have, let me switch. We have two roads mentioned in the problem. The first one is at x equals 0 and y equals 0 as well. And the second one, let's use a different color for this one. And then so let's look at the problem again. So it says a straight road R1 along the x-axis of a Cartesian coordinate system where y is equal to 0 and a smaller parallel road R2 at y is equal to 30 meters. So here, this is at y equals to 0 and this is at y equals to 30 meters. This is R1 and this is R2. A car driver switches on the navigation system and its first reading of the lateral coordinate is y hat equals to 20 meters. So this is the raw coordinate that we obtained from the floating guard data. And this is 20 meters. So 20 meters, so 15 would be somewhere here. And let's say 20 is here. So this is 20 meters. This is the coordinate that we are getting from the navigation system, and navigation system is obviously based on the floating car data. While the true position can only be on the major road or on the smaller road. The vehicle is actually either on R1 or on R2, but the coordinate that the driver got from the navigation system about where he is 20 meters, right? So the difference here between 0 and 20 is 20 meters. So this is 20 meters and this is 10 meters. So naively, if you look at this, it does seem that the navigation system may have made an error of about 10 meters and you are actually on R2 rather than on R1 because in that case, the error would be 20 meters of error. Remember that Newson and Crum uh, they consider a standard deviation of 5 meters. So when we talk about standard deviation and the Gaussian distribution, let's also plot that. So this is just a small depiction of the standard, not the standard, the normal distribution or Gaussian distribution of the GPS noise. So you are getting on x-axis here, you are getting the GPS noise. On y-axis, we are looking at the probability density. And for the normal distribution, mean, median, and mode is in the middle. And because we are looking at the GPS position, we consider that for example, R1, the middle position is representing this y value. So y is equal to 0 for R1, and for R2, it would be y is equal to 30 meters. And the values around this mean position are the GPS positions that we are getting. And this normal distribution is representing all those values that we are getting from the GPS. What we actually got is 20 meters from the navigation system. So consider R1, 20 meters would be somewhere here. And considering R2, 20 meters would be somewhere there. So depending on what particular road segment we are considering at the moment, we are looking at the GPS position and essentially the error in the GPS position that we are getting. Because the driver is either on R1 or R2, but the navigation system is telling us that the value is 20 meters. Next, it says it is known that the GNSS lateral position y hat is unbiased and Gaussian distributed with a standard deviation of 10 meters. So the error that they are considering, the standard deviation that they are considering is 10 meters. Standard deviation, just to remind ourselves, is the average deviation from the mean value. So if this is our mean value, the average deviation on both sides from this mean value is our standard deviation represented by sigma. Mean is generally represented by the value mu. So mu is on the x-axis, sigma is just the deviation, again on x-axis, but it's the deviation around this mean value. So the first part here, and today we will only cover this first part, is calculate the probability P of R1 given y hat. We want to determine the probability of being on the road segment R1 given that y hat is given to us. In this case, y hat is 20 meters that is given to us. That a matching to the major road is correct if no prior information is available. Other than this, we don't have any other information. All we know is that there are two road segments, R1 and R2. Driver is either on R1 or R2, but navigation system is telling us y hat equals to 20. So we don't know which one the driver is on. We want to determine that. So we want to determine this probability given no other information. And so the hint that the chapter gives us here is use the Bayes theorem with the uninformed priors. And they have also given us this information about probability of R1 equals probability of R2, and both of them are equal to half. So we are not given any more information. So we are saying that the chances that you are on R1 or on R2 are equal, and they are 0.5. Probability, just to remind us, goes from 0 to 1. The maximum possible value is 1, which means 100%. So 50% probability is that you are on R1, 50% is that you are on R2. So we need to determine this thing, probability of R1 given y hat. Now, the problem here is that we do not know what is Bayes' theorem. Bayes' theorem comes from statistics, and the chapter never discussed this. Okay, so then we need to look at the solution that is given to us. And we also need to look at Bayes' theorem. So let's actually go to the solution, which is on page 675. And we are also going to look at the Bayes theorem. So the Bayes theorem is here. We have two events, event A and event B, and probability of A given B is given by this Bayes theorem formula. Now, consulting this from the lens of no prior information, we can rephrase this using this formula as the probability of the hypothesis given the evidence. Because what we are looking for is, let me go back to the question first. So we are looking for R1, which is our hypothesis that you are on R1, and the evidence that we've got is y hat. Y hat equals to 20 meters is given to us. So using this formula, we can say that the probability of hypothesis given the evidence would be probability of the evidence given the hypothesis into the probability of hypothesis divided by the probability of the evidence. So first, let's look at this part. This is the probability of the evidence given the hypothesis. Looking at the explanation in the chapter, need to scroll up to map matching section. So this is the probability of our evidence, the geographic coordinates that we are getting, given the road segment Ri, which is similar to the evidence given the hypothesis. Hypothesis here is that the road segment is R1 or R2. So this is the first thing that we need to determine. And this is actually the emission probability. The question, although did not ask about the emission probability, it asked about the opposite of that, the probability of hypothesis given evidence, which is probability of R1 given y hat. But we need emission probability before that. The next part of the formula is this thing, which is the probability of the evidence. Sorry, probability of the hypothesis, which is probability of R1. And then the final part is probability of the evidence, which is probability that you've gotten that geographic coordinate that we obtained, y hat equals to 20 meters. So let's look at the solution now. So here it says, according to the problem statement, the vehicle can only be on road 1 with lateral position y1 equals to 0, or it could also be on road 2 at y2 equals to 30 meters. Since the GNSS position y hat is assumed to be unbiased and Gaussian distributed with a standard deviation sigma of 10 meters, we have the two conditional probability densities. Another concept from statistics, probability density. Let's go back again to Wikipedia and look at the formula of the normal distribution. This formula is the probability density function. We have three things here that we need to plug in this formula to draw one of these uh, probability densities curves or the bell curves. The first thing is the mean value of this distribution. The second is sigma, which is standard deviation. And the third is the value of x. In the context of the problem we are looking at, we are essentially looking at what is the mean value of the position. Excuse me. So we are looking at the mean value of the position. We're also looking at the standard deviation in the position and the actual values of the position that we're getting x. In our case, those are represented by y cap or y hat. So we are getting GPS positions from the navigation system. In the problem, they only gave us one value, but obviously that GPS position is normally distributed because there could be error in the estimated GPS position that we are obtaining through the navigation system. It has a mean, it has a standard deviation. Standard deviation is already given to us. It is 10 meters. That's given in the problem. It's right here, 10 meters. And we would assume that the mean value is going to be whatever is the actual road position. So if you are on R1, on our plot here, if you are on the road R1, then Y value is 0. And that would be the mean value of the position. If you are on R2, then the mean value would be 30 meters. And everything around those two positions would represent the error in the GPS position. If you are exactly on 0 meters, then there is no error. But if you are around 0 meters, that is considered to be an error from the GPS position. So we have information about the mean value. We have information about the standard deviation. X in that formula, or Y in our context, tells us the raw position that we are getting. We have one of those, which is 20 meters. But if we have multiple values from the navigation system, we can actually plot the theoretical probability density using this formula. So this is the probability density function for normal distribution of any variable. But generally, this is standardized. When it is standardized, the formula that is used is this thing. We have an exponential of minus z squared over 2 divided by square root of 2 pi. So square root of 2 pi is just a constant. It is not important. What is important here is z squared over 2. The z squared again is this thing. This is z squared. Z squared is where we are z, the value z is the standard normal value, which tells us, which we can obtain by subtracting the mean value from the raw value divided by standard deviation. So the advantage of standardizing any normal distribution is that the mean value will always be 0 and standard deviation will always be 1. Then those calculations become easy. Have any of you studied probability before?
Yes.
Okay, great. So you may have seen those tables, probability tables, where if you are given a probability value and you're asked to determine the area under the curve, or the opposite, you are given the area under the curve and you are asked what is the particular value of z, right? So those
Yes.
tables come from the standard normal distribution, because regardless of what your variable of interest is, what is its actual mean value from the data that you got, you can standardize it using the value of 0 for mean and 1 for sigma. You can then determine the area under the curve that will give you the probability, right? So it's
Yes.
the same thing that we are using here for determining our probability. But in addition to that, we are also using Bayes' theorem to determine emission probability and also the probability in the question. So once we have this understanding of the standardized normal distribution, phi of z is equal to this thing, or phi of z is proportional to exponent of minus z squared over 2. Now we go back to our solution here, and here it tells us that we have the two conditional probability densities. One is for y1, which is corresponding to the road segment R1. The second is corresponding to R2, which is the related value here is y2. Y1 we know is 0. So here they have skipped it. Y cap minus y1 is not shown here because y1 is 0. But for this formula, y cap minus y2 is shown because y2 in this case is 30 meters. The rest of it is the same formula that we are obtaining, that we have seen, sorry, here. So it's just representing the same formula. They have skipped the square root of 2 pi parts, I think just to simplify things. So it's divided by sigma, but they've skipped that constant value. Phi of this thing is again the standardized version of the normal distribution. Here they explain that standard normal distribution phi of z is proportional to exponential of minus z squared over 2. Again, they have skipped the square root of 2 pi here. So given these two things, we need to estimate these conditional probabilities. And in the Bayes theorem also, we have seen that we need to look at the probability of the evidence. Probability of the it would be the total probability that we obtain from the navigation system, the GPS position that we are getting. So here they say the evidence E is the GNSS position y hat is in the range of y hat minus delta y over 2 and y hat plus delta y over 2. I don't know how they are determining this range, but I think this is an assumption, provided the true position is on the road R1 or on R2. So given that you're either on R1 or R2, the probability of E given R1 is going to be equal to the density obtaining from this formula of y hat into delta y. And the probability of the evidence given R2 is the density of y hat given delta y. I think in simpler terms, without getting bogged by the notation, what it's saying is that given that you are on R1 or that vehicle was on R1, what is the probability of getting these coordinates that we got? What is the chance that you will get these coordinates of y hat of 0 that is given to us if you are on R1? So we can obtain that by getting the probability density using y hat into delta y. Similarly, probability density using y hat into delta y. But the probability density varies depending on either you are on R1 or R2. Here they say the small interval delta y is only introduced to avoid a divided by 0 situation. That's their assumption. And now the Bayes theorem is used. So you have probability of the desired probability R1 given the evidence, or evidence means here the geographic coordinates that we obtained, is equal to probability of y is equal to y1 given the evidence, can be calculated using Bayes theorem. So given that you are on the road network, sorry, on the road segment R1, given, I'm sorry, I'm saying it opposite. Given that you have obtained geographic coordinates that you obtained, what is the probability that you were actually on the road segment R1? And so the same thing that I put here as hypothesis and evidence is now shown here. You have probability of um, evidence or getting the coordinate y cap or y hat equals to 0. given that you are on road segment 1, multiplied with the probability of road segment 1 divided by the probability of the geographic coordinates that we got. And then let's first look at the denominator here. The denominator is using the total probability of getting the evidence or getting the coordinate that we got. It's saying that it should be equal to the probability of evidence given that you are on road network 1 multiplied with the probability of road segment 1 and the same for the road segment 2. This will, in the denominator, this will give us the total probability. In the numerator, we have the same thing as before, that given that you are on the road segment 1, what is the probability that you got the um, coordinates that you got, multiplied with the probability of the road segment R1. And then plugging in those values from these expressions, we get 18%. So here, just to remind us, probability of R1 is equal to R2 is equal to 0.5 is already given in the question. That we are saying that the probability that you are either on R1 or R2 is equal, it is 50%. So those values are plugged in here in the numerator and the denominator, and then probability of E given R1 and probability E given R2 comes from the probability density. That gives us the likelihood of 18%. So this is probability of being on road segment 1 given y cap was 0 is 18%. So 100% minus 18% would be 82%. So for R1, the probability was 18%. For R2, the probability is 82%, which means that it is highly likely that the vehicle was actually on R2 rather than on R1. Looking at our naive solution where we just simply compared the coordinates y of 30 for R2 and the geographic coordinate coming from navigation system of 20, the difference between them is just 10 meters. So naively, we said before that we had a difference of only 10 meters. That's why it is highly likely that you're probably here because navigation system may not be making a huge error of 20 meters. So it is highly likely that you are an R2. So Bayes' theorem also suggests the same thing. So I know this is pretty complicated, and I also do not completely understand this line in the denominator where they are estimating probability of E, the total probability. But the point is that the Bayes theorem also suggests what we naively suggested, that you're highly likely to be on R2 because the error there is less. Any questions? So we can appreciate based on this the problem of map matching. It is a complicated problem where we need to solve this emission probability. We need to determine where exactly is the driver on the road. This will tell us that complete history that Google Maps tell us. So now we can appreciate that hidden Markov model is used and emission probability is used. It's one part of determining the map matching. The second part is transition probability. Transition probability is that we already know, okay, given that you are on road segment 1, what is the chance of getting the coordinates that we got? So once we know that, obviously the vehicle is not going to stay on that particular location. It is traveling, so it's going to go to the next road segment. So transition probability is where are you going to transition to? So transition probabilities describe the likelihood of a vehicle moving between two consecutive candidate road matches, Ri and Ri plus 1. If you were on Ri before, what will be the Ri plus 1 where you are going to go? So if you are on Ri R1, for example, did you then go to R2 or did you go to R3? So looking at our example here, we have three locations, A, B, and C. So we know from raw GPS coordinates what is the exact location A, B, and C. Obviously, it is prone to errors. That's why we need to do this map matching. But from raw GPS coordinates, if we plot it on the map, we get those points, which are not exactly on road segments. Map matching algorithm is about matching them with the road segments, given the knowledge about the road segments. With transition probabilities, we want to know if you were here before, are you going to go, did you go to this road segment next? Or did you go to this road segment next? And then after that, did you go to this road segment next? Or did you go to this road segment next? So from R1, did you go to R2 or did you go to R3? That's what the transition probability is about. Transition probabilities are computed from the driving distance between the projections of the geographic coordinates z onto the road segments R using a shortest path algorithm. For the emission probability, we were looking at air distances. For the transition probabilities, we are looking at the shortest path algorithm between the two segments, between the projections of geographic coordinates onto the road segments. For the emission probabilities, as we discussed before, we were looking at a normal distribution of GPS positions that we are getting. For transition probabilities, they use exponential distribution for these driving distances. Normal distribution is not used here. It's mentioned here the exponential distribution is used. And the way that hidden Markov model try to solve this problem is to consider the objective function of emission probability and transition probability. So the first part is we want to know if you were on a particular road segment R1, what is the chance of getting the value that we got of the GPS value. So we observed GPS value of y equals 0. What are the chances of getting y equals to 0 if you were on R1 or on R2? That's exponential. Transition is once you are determined that you were actually on R2, did you then go to R3 or did you then go to R4? So this is solved by using both emission and transition probabilities as our objective function and optimizing it using Viterbi algorithm. The optimization is looking for maximizing both the emission and the transition probabilities. Pretty complicated stuff, but very interesting. And I think this helps us appreciate the problem that Google Maps and map matching algorithms solve. Any questions before we go to the next point? We only have 10 more minutes.
Nothing from my side.
Okay, so next section is about map match floating card data. And here they have shown us this example where on the x-axis we have time, on the y-axis we have location. And this should look familiar to us because we have used space-time diagrams or time-space diagrams in the trajectory chapter, right? Because we have time on x-axis, location, or the longitudinal position on y-axis, but although the plots look similar, they are telling us different things. For the trajectory time-space diagrams, we had a particular location delta x and a particular time interval delta t, and we knew that all the vehicles that have entered would leave that particular lane for which we are plotting the trajectories. So they would either be entering to that lane, leaving from that lane, or staying entirely in that lane. So we only look at one lane's data when we are looking at trajectory time space diagrams. But when we are looking at the trajectories coming from floating car data, we are relying on more than one vehicle because one vehicle can only show us one trajectory. And these are represented by, if you really focus on this plot, the black lines that are shown here, these four black lines, these are individual trajectories coming from individual floating cars. So every single trajectory, other than these four, they are colored by speed and they are coming from multiple floating cars. So that is only possible when you have multiple cars with sensors and you're collecting data from them. So one way to collect that data, as we discussed the last time, is to use smartphones. Smartphones, everyone is carrying them, and we can get information from their long edge and the short edge, and we know about speed, position, acceleration from smartphone sensors. So here, what they're showing us is, as I said, multiple vehicles, and this is the areas of motorway interchanges with off ramps and subsequent on ramps, characterized by horizontal areas with lower floating car data density. So here we see, in some cases, for example, here this is very exaggerated, where we see that there's some relatively uh, um, smaller slope values of these trajectories, which tells us that this is where the vehicles have slowed down. We can also confirm that by looking at the speed uh, color here. So red here represents stopped vehicles or very slow vehicles. And they also mentioned traffic breakdowns and various patterns of congestion. We can clearly see traffic breakdowns here. We also see traffic breakdowns in this area as well as in this area. The purple and the blue lines represent higher speeds, as we can see here. Another important point is that the floating car data generally does not distinguish between different lanes. So as I said before, trajectory data generally look at time-space diagram for a given lane, but floating car data does not. Here, we do not know what lane each of these vehicle trajectories were on. So this could be a combination of multiple lanes. It could be one lane depending on where the floating cars were. Another important aspect here is the travel time. So travel time is one of the uh, good things that we can get from the floating car data. The realized travel time is the time a vehicle needs to travel through a road section at the time of leaving it. Travel times can be determined directly from the trajectories of floating car data driving through the entire section, such as the highlighted ones that we've seen in the black lines. And let's see, right here in this plot, we can see the lines represent the average and the points represent the individual floating car data points. On x-axis, we have time. On y-axis, we have realized travel times. So we can see from multiple floating car data points that we are getting on this plot, we can see that, for example, at 2 p.m., right here at 2 p.m., we have this peak in the travel time, which means that uh, vehicles were taking longer to travel. Then, similarly, at about 5 p.m., we have another peak. So, this represents the peak hours. And then here, the second plot is the average travel speed, which we can also obtain from, let's see, right here. So once you have the travel time and we know the distances that the floating cars has covered, we can determine the average travel speeds. They're also plotted right here. So floating car data can tell us a lot about the travel times, and another thing is the speed, average travel speeds. And then figure 4.7, let me see, that we have already discussed. Figure 4.8 is discussed in this section aggregation on link level. Actually, before figure 4.8, I highlighted here the speed of trucks and the traffic jams, which are also mentioned in figure 4.6. So, for example, actually in figure 4.7, we can see I highlighted here that this is the speed of trucks. So we see this cluster of floating car data points that represent that these are trucks, and the other cluster here represents cars. Then traffic jam is depicted in figure 4.6a, leads to an about 3 times higher travel time with strong variations for individual vehicles between 40 and 60 minutes. So figure 4.6a is shown here. This is the zoomed in part from figure 4.5. And this is, as we discussed before, showing us local speeds because we can estimate it from this time-space diagram, and we can clearly see that this is a traffic jam in both of these parts. Okay, figure 4.8 is, so on the top of figure 4.8, we have the speed on y-axis and hour of week on the x-axis. So on a given day and in a given hour, we can get data from multiple floating cars and we collect that data. Those data points are shown here as the gray points, which are not very clear. Let me zoom in a bit, but this is representing these shades that we see. These are actually points which are plotted in a way that they are transparent so that they are not plotted on top of each other. And we can see that there are multiple of those points. There's so many that they have used a lighter transparency level so that we can see that they are there. But then arithmetic mean and harmonic mean of these speeds are obtained. Remember from, I think, first or the second chapter, we discussed harmonic speeds, harmonic mean speeds, and arithmetic mean speeds. Those are obtained here using the floating car data. So these lines tell us a story about what is happening on weekends and on weekdays. So we can see, for example, on Saturday and on Sunday, the speeds seem to be slightly higher. Both the harmonic and the arithmetic mean speeds are slightly higher than the speeds that we get on weekdays. Similarly, on the same day, on a weekday, we can see that there are dips. So, for example, between 0 to 24 hours, we have Monday, and we see this dip in the speed, which is representing the morning peak hour, I believe. And then we have another morning peak hour for the next day, for Tuesday, and it goes on until it shows us the weekends. We also see standardized counts of the vehicles. So this is counting how many floating car data points we got, and then dividing it by all the number of floating car data points for the entire time series. So that gives us the standardized counts. So this is telling us that on weekends, Saturday and Sunday, the peak is smaller than the weekdays. Obviously, there's more travel here. And also notice here that these two plots are for motorways and these two are for the city. So for city, we do see there's a peak for Saturday. So there are still a lot of floating cars moving in the city, but a very small peak on Sunday in the city. On motorway, we see a relatively higher number of counts, and that is expected because people travel intercity when they are um, over the weekends. So that is expected. All right, so it is an hour now. Any questions?
But can we know like how these diagrams have been drawn?
So these are obtained from, they mentioned here, courtesy of TomTom. TomTom is an API that provides this floating guard data. So they have estimated it from those data, but they have not shown us how the harmonic and arithmetic mean speeds are estimated. But that information is given to us in the previous chapters. So they've used those formulas for estimating